In this lecture, we will consider the elements of machine learning framework, one element of the machine learning framework more carefully. This is a bit theoretical lesson, but we will also consider practical aspects. We'll consider the error measurements of machine learning. Recall that we have four important elements in the framework of learning: the data, the hypothesis set, the algorithm, and the algorithm of selecting the best hypothesis from the family, and the criteria according to which the algorithm makes the makes the selection. In previous discussions, whether when we were discussing theoretical algorithms or data models, or we were considering the practical implementation of the algorithms, we took this loss as granted because for most of the tasks, the semantic or the meaning of the loss is pretty clear according to the definition of the task. And we take a pragmatic view at this part. We calculate the cost of each hypothesis with respect to the training data and let our algorithm select hypothesis according to this. Now in this lecture, we will give this part a little bit more consideration, which will help us to reveal more aspects about the entire random process of machine learning. The machine learning is a random process. Now let us realize that this loss function its actual rule when it is deployed here is to measure the difference between two functions, and the two functions are two maps from the x space to the y space. One function is the one that underlaid the generation of the data, and on the other hand, the other function is the individual hypothesis in the hypothesis family. So this loss should be functionals. Given two functions, it returns the difference between them. This sounds abstract. How can you measure the difference between two functions? Because functions sounds like some amorphous, some complex objects. It's not like two numbers for which you can simply do a subtraction and take the difference. Let's consider an example. See if the x is just a one-dimensional variable, which perhaps the simplest x that can be, and the function maps x to the value. I should have put an y here, but you understand that is the value corresponding to each x. And the map is from real value to real value. It is natural to think that the difference between these two functions, one represented by this greenish, bluish green line, and the other by the dark red line curve, should be the areas enclosed by the difference of these two curves. It is not very difficult to understand, to imagine, to compute such difference, the area. It is very natural to consider the the way when we do calculus, when we calculate the area, we can scan all possible values of x and consider the approximate rectangle areas at each x value with a very slight change of x. So one aspect of the error function is the definition of pointwise error. That is to measure the difference between the predicted value at x and the ground truth value. I use f to represent ground truth value of x. On the other hand, to measure the average difference between, I have already said that. To measure the difference between two functions, it is not only the pointwise error is concerned, it is the average or the overall error over the entire x space, entire data space that we are really focused on. So this view gives us, forces us to consider the learning framework with a bit more depth. This is the original framework. With the overall error point of view, we can now understand that the black box of data generation can be modeled in this process. We have a black box of both the data space and another unknown distribution of the data. So using the distribution, we can have samples, x samples from the data space, and there is another unknown mapping between x and y, so that the unknown distribution on the data space generate x samples, and these samples are processed by the unknown function, unknown ground truth mapping from x to y. And this process gives us the data samples of x1, y1 to xn and yn. Taking this view, we have the loss defined as an integral over all x on the x space, and at each x we take the pointwise definition of the error, and the integral is over all x, weighted by the probability or the likelihood of a data sample can rise at different x values. And we must immediately realize that this definition is a theoretical one. Ideally, we can optimize this loss function, but in practice, we can only optimize its delegate. What's delegate? For the pointwise definition, we probably don't need to do any compromise because we can define that, and the computation is probably simple. What we need to compromise is that because the distribution is unknown, therefore we can only be satisfied with talking about difference at the points we actually observed. We don't know the points we didn't observe. We don't know the probability at those points. We don't know the real value of the unknown ground truth function at those points. So this, on the left hand side of this slide, I show the ideal definition of the loss function. that is integral over X space using the weighted by the probability, unknown probability distribution of X, which is actually taking expectation over X and take the difference between the predicted value and the value by the unknown ground truth. On the right hand side of the slide is what we actually practice in learning algorithms. We optimize a delegate of this unknown ideal loss function. The delegate can only look at n data values, n trained samples, and evaluate the error of the prediction at this n data values, compare the prediction at each individual data sample with the given y value, the known target value at the samples. And the hope is that this function, the value of this delegate will track the value of this, at least when we have reasonably many data samples.